methods, you can arrive at the solution of quantum mechanical problem in the microscopical particles. So, in classical physics, the description of particles through Newtonian mechanics or that of waves using wave equation are accomplished through differential equations only. New formulation should be incorporated so that the features of wave particle duality, uncertainty principle, and black body radiation, etc., spectrum of black body radiation, etc., could be understood. At the same time, it should reduce the classical formulation under appropriate limit. So your Schrodinger's wave mechanics and Heisenberg matrix mechanics were major steps towards this, which I have explained you yesterday. In Schrodinger formulation, like that of Newtonian mechanics, a differential equation describes the system under the considerations. However, the differential equation in the Newtonian mechanics is different from that of the Schrodinger formulation, and this is known as Schrodinger equation. And the Schrodinger equation is regarded as the starting point of the quantum description of a physical system. Similarly, your Heisenberg's formulation starts with operators or matrix formulation of the initial wave equation, and you can describe the physical system in microscopic world by using that formalism. So let us discuss Schrodinger formalism first. And as I have explained you today, that Schrodinger equation is a differential equation. So let us have the simplest form, time-dependent Schrodinger equation in one dimension, which I was explaining you yesterday also. Am I audible?
Yes, sir.
So let us consider a non-relativistic free particle of mass m moving in x direction. And you know, non-relativistic particle is a particle whose velocity is very, very small than that of velocity of light or c. And free particle is a force-free particle. You have no forces exerted upon a particle, and the particle will be called free particle. In other way, there is the potential V in the region where the particle is situated is 0. So the simplest case to one-dimensional case is in x direction the motion of the particle. Let us consider, since it is a free particle, so the energy is entirely kinetic. So the energy is entirely kinetic. There is no potential energy. So A E is equal to px square by twice m, where m is the mass of the particle and px is the momentum of the particle when it travels in a direction I cap direction or in x-axis. So px is a linear momentum. So yesterday we are discussing de Broglie formulation. The French physicist de Broglie proposed that in microscopic world, the matter behaves both like particle and wave. So the particle characteristics of the matter is represented by lambda, and wave the particle characteristics of the microscopic particle characteristics in the microscopic world of the matter is represented by P or momentum, and wave characteristics of the matter in the microscopic world is represented by the behavior that is lambda, or the feature that is lambda. So lambda is equal to h by p, where h is the Planck's constant. So both particle behavior and wave behavior is contained in the de Broglie equation. So now your in de Broglie formulation, the free particle is associated with a plane wave, and the form of the plane wave is like a e to the power I k x multiplied by x minus omega t is equal to a e to the power I by h cross px multiplied by x minus e multiplied by t, where px is the momentum, x is the position, e is the energy, t is the time, and I is the I is a complex number root over of -1, and your a is the amplitude. Okay, so Planck's constant H is nothing but 6.626 into 10 to the power minus 34 meter square kg by second. And your omega is the angular frequency. So energy E can be expressed as H cross omega is equal to Px square by twice m. This plane wave cannot represent a localized particle. A localized particle in X space is represented by a wave packet constructed by superposing a large number of plane waves. So localized particle, uh, localized particle, uh, localized particle, if you discuss, it is represented by a plane wave, and localized particle in X space is represented by a wave packet, not a wave. So your wave function psi will never represent a particle or localized particle. Only the superposition of a large number of waves, which is called wave packet, and in a localized region represents a particle. And we shall discuss it in your Max Born formulation or Max Born's interpretation of wave function. So here your localized particle, as I have explained you, is represented by a wave packet. So wave packet can be represented by psi x comma t is equal to integration minus infinite to infinite your a, which is a function of px, then e to the power I by h cross px multiplied by x minus e multiplied by t dpx. Writing a px is equal to 2 pi h cross to the power minus half phi, which is a function of px. For future convenience, we can write psi, which is a function of x comma t, is equal to 1 by 2 pi h cross to the power half integration minus infinite to infinite phi, which is a function of px, e to the power I by h cross px x minus et dpx. So your phi, which is a function of px, is regarded as the amplitude of the component wave of a momentum px. It is independent of time t. So our task is to obtain a differential equation satisfied by psi regardless of phi. So the differentiation of psi, which is a function of x comma t with respect to t, gives del psi by del t is equal to 2 pi h cross to the power minus half integration minus infinite to infinite dpx minus I e by h cross phi, which is a function of px, e to the power I by h cross px multiplied by x minus e multiplied by t. So your del psi by del t will be represented by 2 pi h cross to the power minus half integration minus infinite to infinite dpx e phi e to the power I by h cross px multiplied by x minus et. So if you differentiate psi twice with respect to your x, you can obtain del square psi by del x square is equal to 2 pi h cross to the power minus half integration minus infinite to infinite dpx minus px square by h cross square phi e to the power I h cross square multiplied by phi x minus et. Px minus et. So your minus h cross square by twice m multiplied by del square psi by del x square is equal to 2 pi h cross to the power minus half integration minus infinite to infinite dpx e phi e to the power I by h cross px x minus et. So now you compare these two equations and you can get I h cross del psi by del t, where psi is a function of x comma t, is equal to minus h cross square by twice m del square psi by del x square. So this is the time dependent Schrodinger equation for a free particle in one-dimensional configuration space, that is X space. It can be written in the form I h cross del by del t psi is equal to 1 by twice m h cross by I del by del x multiplied by h cross by I del by del x of psi. So I h cross del by del t, which I was explaining you yesterday, is nothing but energy operator. So energy operator E cap psi is equal to px cap square by twice m psi, where h cross by I del by del x represents momentum operator px cap. So your E cap can be represented as I h cross del by del t, and px cap is represented by h cross by I del by del x. So your E cap psi is equal to px cap square by twice m psi is Schrodinger equation operator formalism or Heisenberg picture. and your I h cross del psi by del t is equal to minus h cross square by twice m del square psi by del x square is the Schrodinger equation, differential equation, and it represents the Schrodinger picture. So this equation can be obtained from classical energy momentum relation, that is E is equal to px square by twice m. Okay. And allowing E cap and px square by twice m to act on the wave function psi. So while acting on the configuration space wave function psi, you under px cap behaves as differential operator h cross by I del by del x, and E cap behaves as differential operator I h cross del by del t. So this is time independent Schrodinger equation for free particle. If the particle is not a free particle, so you have to include the force in the expression. Am I audible?
Yes, sir.
So your force Fx, your force in one dimension Fx can be written as minus del by del x for u, which is a function of x comma t. So u is the potential energy of the particle, which we are taking as 0 or in case of free particle. So now the particle has both potential energy and kinetic energy, and your E can be represented as px square by twice m plus u. It is very similar to that of classical mechanical equation. Utilizing the operator correspondence depicted in the earlier equation and writing u is equal to u cap, you can have your IH cross del psi by del t is equal to minus h cross square by twice m del square psi by del x square plus u psi. I think you know, you have read all these in your BSc honors days. Am I right? Am I audible?
Yes, sir.
Yes, sir.
So your IH cross del psi by del t can be written as h cap psi. So our h cap is equal to minus h cross square by twice m del square by del x square plus u, and h cap is called the Hamiltonian operator for motion of a particle in one-dimensional space. So our E cap psi is equal to h cap psi if we include the force. So your energy operator operated upon the wave function psi gives the Hamiltonian operator upon the wave function psi, and if it is in force force free region, then your E cap is equal to px cap square by twice m psi. So your time dependent Schrodinger equation. Consider a non-relativistic free particle of mass m, velocity u, and momentum p. Its energy is entirely kinetic, as E is equal to p square by twice m. So time independent Schrodinger equation in 3 dimensions. So you replace px by p vector and x by r vector, and del square by del x square is equal to delta operator. So now your wave packet will be represented by wave functions, superposition of wave function, and psi r comma t is equal to integration from minus infinite to infinite a, which is a function of momentum p, e to the power I by h cross p dot r minus et dqp. So by proceeding in the similar way as I have described you in one-dimensional case, and which is shown in the screen, you can arrive at the expression IH cross del by del t psi is equal to minus h cross square by twice m del square psi, where del square is the operator, where del square is nothing but del square by del x square plus del square by del y square plus del square by del z square. So your h cross by I del operator is your momentum in 3 dimension momentum operator, and IH cross del by del t is your energy operator. Similarly, you have the, when you include the Hamiltonian, you have Hamiltonian operator h cap minus h cross square by twice m del square plus u cap. Okay. Your Schrodinger equation is a single particle differential equation. It is first order in time derivative. So the time evolution of psi bears more resemblance to the diffusion or heat conduction equation than to the propagation of elastic waves. It is a linear equation as it does not contain higher powers of psi or its derivative. Then dynamical evolution of quantum state. The time evolution of a quantum state represented by a wave function psi is described by the time-dependent Schrodinger wave equation. So the wave function of a quantum state depends on position and time and contains all information about the system in that particular position and time. This state wave function obeys the time-dependent Schrodinger equation. So knowing the initial conditions and the boundary conditions, the state wave function of the quantum system can be determined through the time-dependent Schrodinger equation at any arbitrary time. Hence, the dynamic evolution of the quantum state can be studied. So what are the properties of wave function? A wave function, a psi, which is represented by psi, is a parameter varying with both position and time. So it is both time dependent and position dependent. And it describes the wave associated with the material particle. The wave function expresses the probability distribution of a particle in space and time, just as electromagnetic wave describe the distribution of electric and magnetic fields in space and time. According to Du Bois, a moving particle is associated with a wave known as matter wave. Hence, a wave function mathematically describes the wave characteristics of a particle and the probability distribution of the particle at a given point in space and time. The wave function is represented by symbol psi. Therefore, the wave function is not an observable quantity. The wave function is also called a state function because it gives information about the state of a physical system in accordance with the rules of quantum mechanics. A wave function can be defined as a solution of the Schrodinger differential equation and provides a complete quantum mechanical description of a particle. Okay. Now the Max-Born interpretation of the wave function, which is known as the physical interpretation of wave function. So Max-Born interpreted the physical significance of a wave function by comparing a beam of matter particles with a beam of photons. Consider a beam of light or photons having intensity I, incident, normal on a screen. Am I audible?
Yes, sir.
So if capital E is the electric field of the beam, then the intensity of the beam at a point can be written as I is equal to C epsilon 0 E square, where C is the velocity of light and epsilon 0 is the permittivity of free space. So your I is directly proportional to E square. So from the particle point of view, the intensity of light beam of given frequency is proportional to the number of photons n that passes through a given area per unit time. So your I is directly proportional to n. So from the above definition, the intensity, the above definition of intensity, we have here capital N is directly proportional to E square. So the number of photons reaching the screen is proportional to the square of the electric field strength E. This relation is valid only when a large number of photons are involved. If we are dealing with only one photon, the above relationship N directly proportional to E can be interpreted in a slightly different way. At all points, the square of the electric field strength, that is E square, is measure of probability that a photon will be at the location. So at points where E square is larger or very large, there is a high probability of the presence of photon and vice versa. Similarly, for matter waves, if psi describes a collection of many electrons, then modulus of psi square at any point will be proportional to the number of electrons expected to be found at that point. If psi represents a single electron, say an atom, then modulus of psi square represents the probability of finding an electron at a given position and time. So your modulus of psi square is often referred as the probability density or probability distribution. So if we summarize, Born's interpretation of wave function can be summarized in the following points. First, Max Born interpreted the wave function psi for matter waves is analogous to the electric field capital E for electromagnetic wave. So wave function is analogous to electromagnetic wave. The wave function psi is called the probability amplitude and is complex quantity, and therefore it is not a measurable quantity. You cannot measure a complex quantity. You can measure only a real quantity. And your wave function psi is a complex quantity. So it is not a measurable quantity. And it is a probability amplitude only. It is a probability amplitude only. And the product of psi star is equal to modulus of psi square is called the probability density, which is a real quantity. Psi star is a real quantity because it is modulus of psi square. And it expresses the probability of finding the particle at a given position and time. It is always a real and positive number, and hence is an observable quantity. So psi cannot be observed, but psi square can be observed, and it is nothing but the probability of finding the particle at a particular position. The greater the value of psi square, the higher the probability of finding the particle at a given point and time. The probability that a particle may be found in a region between x and x plus dx at time t is p dx is equal to psi star psi dx is equal to psi square dx, where p is a function of x comma t, psi star is a function of x comma t, and psi is a function of x comma t. And your psi square, which is nothing but psi star psi, is equal to p is the probability density. And the last part is, or the last interpretation is, the wave function used here is a normalized wave function. That is, the volume integral of psi square over all space is unity. Your p is equal to integration from minus infinite to infinite psi square dx is equal to 1. P is equal to integration minus infinite to infinite psi square dx is equal to 1. Then let us discuss probability and probability current densities in 3 dimensions. So rho dqr is equal to psi square dqr is the probability of finding the particle at time t at the location r vector in the volume element dqr. So the total probability of finding the particle somewhere in space is either 1 or 100%. So integration psi star psi dqr is equal to 1. For 1 dimension, the probability of finding the particle between the points x1 to x1 and x2 is equal to the sum of probabilities rho dx in the infinitesimal interval between x1 and x2. It is thus represented by rho is equal to integration from x1 to x2, rho dx is equal to integration from x1 to x2 psi square dx. The probabilistic interpretation of psi can well appreciated if and only if the probability is a conserved quantity. That is, if the probability of finding a particle in some bounded region of space decreases in time, then the probability of finding it outside that region must increase by the same amount. We thus expect an equation of continuity depicting conservation law. We also expect a related quantity called probability current density, which is analogous to the current density in electrodynamics. Suppose that psi represents a one particle system. So the probability of finding the particle in a finite volume omega bounded by a surface area A is rho is equal to integration over omega psi star psi dqr. So the probability flow across the surface A is determined by the time rate of change of probability. So time rate of change of probability can be represented as dp by dt. So your dp by dt is equal to integration over omega del psi star psi by del t dqr, which is equal to integration over omega psi star del psi by del t plus psi del psi star by del t dqr. So from Schrodinger equation for psi and psi star, we get del psi by del t is equal to I1 by I h cross multiplied by minus h cross square by twice m del square psi plus u psi. and your del by del psi star del t is equal to minus 1 by I h cross minus multiplied by minus h cross square by twice m del square psi star plus u psi star. So you can write dp by dt in a form as shown in the screen, and by using the identity del f del g is equal to del f dot del g plus f del square g, you have your continuity equation dp by dt is equal to minus integration over omega del dot j dqr, where j is h cross by twice mi psi star del psi minus psi del psi star, and probability of finding the particle in a finite volume omega is p is equal to integration over omega your rho dqr is equal to integration psi star psi dqr, and your dp by dt is equal to d by dt of integration p dqr rho dqr is equal to integration over omega del rho by del t dqr. So combining these two equations, we can arrive at the expression integration over omega del p by del t plus del j del dqr is equal to 0. The volume omega over which you integrate is arbitrary. So we can hold, it can hold good, equation can hold good if and only if the integrand vanishes. So your del rho by del t is equal to del j is equal to 0. This is the equation of continuity. So what it describes? The equation is encountered in electromagnetics as well as hydrodynamics. In electromagnetics, your rho and j respectively represent the charge density and current density. So a rho is equal to psi star psi represent the probability density. So therefore, we can recognize j as the probability current density. We further notice that by applying Gauss divergence theorem, we can write dp by dt is equal to minus integration over a j dot n cap dA, where n cap is a unit vector in the direction of dA. So the equation of continuity can be written in the form plus minus del rho by del t is equal to minus plus del dot j, and your plus minus del rho by del t dqr dt is equal to minus plus del dot j dqr dt. So this equation implies that an increase or decrease in the probability density through infinitesimal volume dqr in time dt is equal to the decrease or increase of the divergence of the probability current density through the same volume dqr in time t. In other words, an increase or decrease in the probability within a given volume leads to a decrease or increase in the flux of probability current through the boundary area during a given interval of time. So what is the conditions for physical acceptability of a wave function? If for the state del dot j is equal to 0, then del rho by del t is equal to 0, and your rho is constant in time. That is, the probability density is conserved. If your rho is equal to psi square, determines the probability per unit volume of finding a particle in space. So your psi must be single valued, continuous and finite. It follows from the equation of continuity that psi must have a continuous and finite except at singular points first derivative. The wave function psi must vanish at infinite. So here are some examples from which you can calculate your probability density, probability current density, and the formula how to calculate this. The normalization of psi. So psi star psi dqr is equal to 1 is called normalized wave function. If psi star psi dqr is not equal to 1, then it is not normalized. So what it physically means? Anybody? What is meaning of normalization? Am I audible?
Yes, sir.
What is normalization? If the wave function is normalized, then there is 100% probability of finding that particle in that region. If the wave function is not normalized, there is less than 100% probability of finding that particle in that region. So if your psi star psi dqr is equal to 1, then it is, you can definitely find the particle in that region where your integration psi star psi dqr is equal to 1. And if it is less than 1, it can never be greater than 1. If it is less than 1, then you have less probability of finding that particle in the region. So if you have certain wave function where psi star psi integration psi star psi dqr is not equal to 1, how to make it 1? This is the method of normalization. So you have to multiply it with the root over of n. You have to multiply it root over of n, and it will be normalized. Okay. So let us have
Yes,
an
sir.
example. Your psi is equal to psi 1 by root over of n, and your this is an example C. Normalize the wave function psi is equal to a to the power I k x over the region minus a smaller equal to x smaller equal to a. So your integration minus a to a psi star psi dx is equal to minus a to a star e to the power I k x a e to the power I minus I k x dx is equal to minus a to a star a dx is equal to 1. So assuming a to be real, we have a square integration minus a to a dx is equal to 2a capital A square is equal to 1. So a is equal to 1 by root over of 2a. So the normalized wave function is psi is equal to 1 by root over 2a e to the power I k x. Are you getting it?
Yes, sir.
Similarly, find the norm of a particle described by the Gaussian wave packet. Wave function psi is equal to a to the power minus alpha square x square by 2 multiplied by e to the power I k x in space, in all space. So this is how you can have it. Your norm a is equal to root over of alpha by root over of pi. Okay, so you can go through this. Then linearity and superposition principle. The superposition principle is also known as principle of linear superposition of quantum states. This principle is a consequence of the linearity of the Schrodinger equation. So if your psi 1 and psi 2 are two solutions of the Schrodinger equation, then a linear combination psi is equal to C1 psi 1 plus C2 psi 2, where C1 and C2 are constants, are also the solution of that Schrodinger equation. And in generalizing it for n solution, you can write psi is equal to C1 psi 1 plus C2 psi 2 plus C3 psi 3 plus so on forth. Cn psi n is equal to summation n is equal to 1 to n Cn psi n. So if psi n are solution of the Schrodinger equation, then their linear combination is also a solution. Okay, so you can prove it as shown in the screen. It is very simple and straightforward. Then operator. Any unambiguous rule by which one function is changed to say some other function is called an operation. The abstract representation of such a process is called an operator. So an operator represents a mathematical operation that transforms one function into another. An operator for observable q is denoted by placing at cap, hearts or carets sign over q. And you can have a q cap f, which is a function of x, is equal to gx. So q cap is an operator which acting on the wave function f to and transform it to gx. So it is defined over a class of functions, and your equation looks like a product. Indeed, it is a product when q cap is a number or some given function of x, real or complex. Okay, so eigenvalue and eigenfunction. So a operator a cap acts on a well-defined wave function psi, and the results is the same function psi multiplied by a constant. Then psi is an eigenfunction of the operator, and a is the eigenvalue of the eigenfunction psi. The corresponding equation is a cap psi is equal to small a psi. So if a cap is equal to p cap, then you're in the right hand side you will have p psi. So your p will be the momentum eigenvalue, and p cap is momentum operator. Similarly, if in the left hand side you have E cap psi, in the right hand side you have some a value multiplied with the wave function, and that value is called energy operator. If you have H cap in the left hand side, the psi is having with a coefficient, and that coefficient is nothing but Hamiltonian eigenvalue, so on and so forth. Okay.
Yes,
Linear
sir.
operator. Q cap is called a linear operator if Q cap psi 1 is equal to phi 1 plus, and Q cap psi 2 is equal to your phi 2. Imply Q cap lambda 1 psi 1 plus lambda 2 psi 2 is equal to lambda 1 phi 1 plus lambda 2 phi 2, and your lambda 1 lambda 2 are constants. So a linear operator is said to be completely defined when the result of this application to every function is given and your operator like k e to the power I theta, d by dx, e cap, px cap, your p cap, and these are very much important in quantum mechanics. Null operator. A linear operator is considered to be null if your q cap psi is equal to 0. Unit operator. If q cap psi is equal to psi, then algebra. Equality. If a cap psi is equal to b cap psi, then your a cap is equal to b cap. Addition. A cap plus b cap psi is equal to a cap psi plus b cap psi. Product. A cap b cap psi is equal to a cap multiplied by b cap psi. Okay, commutation. A cap b cap minus b cap a cap is equal to 0. And you can write it in a square bracket, and it is called commutator bracket of the operator. So the operator a cap b cap are set to commute. If a cap b cap, that is a cap b cap minus b cap a cap is not equal to 0, then it do not commute. Okay. Then commutation relation between position and momentum operators. This is in coordinate space and momentum space. In the configuration space, let the wave function represent the state of the particle be psi, and in the momentum space, that the wave function represent the state of the particle as phi. So you have your rj cap psi is equal to rj cap psi, and your rj cap phi is equal to minus h cross by I del phi by del pj. So your rj cap is equal to h cross by I del by del rj, and your rj cap is equal to minus I h cross by I del by del pj, and pj cap is equal to pj. Similarly, you have commutation relation between operators of R. Your rj cap, rk cap commutation will give you 0, and rj cap, rk cap commutation will give you 0. So we thus conclude that rj and rk commutation will give you 0 when j comma k is equal to 1, 2, 3, and similarly x comma y, y comma z, and z comma x in the commutation relation will give you 0. Then commutation relation between operators for components of momentum and coordinate space. So pj cap comma px cap is equal to 0. Pj cap px cap in momentum space is also 0. Commutation relation between operators and different components of R and P. Rj cap comma pk cap is equal to IH cross del jk, where del is jk is Dirac delta function. Similarly, in momentum space, your rj cap comma pk cap is equal to IH cross del jk. So you can see both in if you change the coordinates, the coordinate space, your the operator algebra will not altered. Okay, in coordinate space, what you get in the momentum space, you can also get the similar results. Then commutator algebra, you can go through this. A cap comma a cap is equal to a cap minus a cap is equal to 0, and other things. Here is an example: x cap comma px cap is equal to IH cross. Your x cap comma px cap psi is equal to x cap px cap psi minus px cap x cap psi is equal to x h cross by I del psi by del x minus h cross by I del psi x psi by del x. This is nothing but IH cross psi. So your x cap px cap is equal to IH cross. Then your Hermitian operator. In quantum mechanics, a physical quantity q is represented by a linear operator q cap. The expectation value of q in the state psi is given by your bracket q is equal to integration of psi star q cap psi dqr, where psi is a normalized wave function. So the expectation value of q in the state psi is a real quantity. Thus, your q is equal to q star, but q star is equal to your integration psi star q cap psi dqr star, and which is integration q cap psi star psi dqr. So this implies that integration psi star q cap psi dqr is equal to integration q cap psi star psi dqr. So operator satisfy this equation is called Hermitian operator. Any operator represents a physical observable. So Hermitian operator operated over a wave function. If it satisfies this relation, then it represents a physical. Any operator represents a physical observable must be a Hermitian. Then your expectation value. In general, the outcome of a measurement in quantum mechanics is a random variable with many possible values. The average of these values is called the expectation value and can be found out by the formula given in the screen. Your average value of x is equal to x1 plus x2 plus x3 plus so on so forth xn by n, and this is the expectation value, that is summation I is equal to 1 to n xi by n. So if the value x1 appears n1 number of times, x2 appears n2 number of times, and so on, xn appears nn number of times, then the above equation can be expressed as shown in the screen. So your expectation value of x is equal to summation I is equal to 1 to n xi pi. So the general features of the general formula for expectation value shown in the screen. The expectation value or average value of any observable q is expressed as q average or q expectation is equal to integration from minus infinite to infinite your psi star q cap psi dx. In 3 dimension it will be dqr, and if it is normalized, integration psi star psi dqr is equal to r. Then your expectation value position, momentum and energy. So your position, it is minus infinite to infinite, psi star x psi dx. For momentum, it is minus I h cross integration minus infinite to infinite, psi star del by del x psi dx. And for energy, it is I h cross integration minus infinite to infinite, psi star del by del t psi dx. And here is an example how to find the expectation value momentum for a particle described by the wave function. So these are the equations. Then wave function of free particle, psi is equal to a e to the power I by h et minus p dot r. Then time dependent Schrodinger equation, time independent Schrodinger equation. Previous was time dependent. Time independent matlab there will be no t term, del by del t term. So this is the derivation, and the expression is in one dimension is that d square by dx square plus d square by dy square in 2 dimension. Your psi plus twice m by h cross square e minus u psi is equal to 0. And in 3 dimension, you have your d square by dx square plus d square by dy square plus d square by dz square psi plus twice m by h cross square e minus u psi is equal to 0. So your del square psi is equal to twice m by h cross square e minus u psi. I have explained you what is the energy eigenvalue and energy eigenfunction. Then about the Hamiltonian, then Schrodinger solution of Schrodinger equation in spherical polar coordinate system. Then stationary states. The quantum state for which the probability density is independent of time are called stationary states. So the quantum state where the probability density is independent of time. The solution of the Schrodinger equation here is psi is equal to psi e to the power minus I et by h cross. The probability density P will be your psi star psi is equal to your psi star e to the power I et by h plus psi e to the power minus I t by h. So the your e to the power I and minus I term will cancel out, and your probability will be psi star psi. Okay, it is t independent, time independent. So it is called a stationary state. Okay. Then your evaluation of a Cn, that is expansion of an arbitrary wave function as a linear combination of energy eigenfunctions. Then physical significance of Cn, it represents the probability amplitude, probability of finding the value Qn when Q is measured. Then your completeness relation, every physical quantity can be represented by a Hermitian operator which has a complete set of orthogonal eigenfunctions. Then use closure relation as shown in the screen. Summation n psi star n r vector cap r vector dash is equal to psi n r vector del r minus r dash, where del is Dirac delta function. Then the general solution of time Schrodinger equation in terms of linear combination of stationary states. Then your velocity of de Broglie wave and phase velocity, wave velocity, non-relative motion, dependence of phase velocity and wave velocity. U is equal to c e 1 plus m0 square c square lambda square by s square to the power half. So it behaves like a dispersive medium because it is dependent upon the wavelength. Then superposition of two waves. and how you can have your wave packet, which represents a particle. Then groove velocity, then Gaussian wave packet. Okay, am I audible?
Yes, sir.
Okay. So I think let us have a break, and you have a cup of tea. After that, we shall then continue. Is it okay, or shall I continue? Am I audible?
Yes, sir.
Yes, sir.
So I think a cup of tea will refresh you, and we can have these things in Hilbert space or Heisenberg formulation, and then we shall go to the applications. Or if you want that I shall continue, then I can also continue now. Okay.
Okay.
Okay, sir.
So is the screen visible?
No, sir.
No, sir, not it.
Is the screen visible now?
Yes, sir.
So I was explaining this in yesterday class. So in the first part of today's class, we have discussed in detail the Schrodinger picture. Now we shall discuss the Heisenberg picture and the wave function in a Hilbert space. Okay. So let
Okay,
us
sir.
meet after some time. Okay. And if
Okay,
more
sir.
people will join, then you can also call them. So around after 20 to 30 minutes, or if you say earlier also. Earlier we
Sure,
can
sir.